Good morning. What I have for us today is, as you can see on the screen, another look at the NEON data, the National Ecological Observatory Network. And what I hope to do today is to make a quick video about how to download the data. For our biostatistics course, Bio 175, we'll be focused on this NEON data for the last month of the course, or in other words, starting up the final project in a couple weeks. I fully admit that we will be looking at this tutorial that's on the Neon Science website about how to download and export the data using R in RStudio. I'm going to create a new R Markdown document. And this document will be available on our Canvas page when I'm done here. And let me go ahead and save this as Bio 175, Neon, etc. Something that we looked at before is that to use the Neon data, there are helpful packages that will bridge the gap between RStudio and Neon. So those include the Neon utilities and also some functions coming from Bioconductor. If need be, if you haven't done this before, you would need to install these recommended packages. And recall that in order to install a package, type in the install.packages code down here in the bottom left, down in the console, and you only have to run this once. So each one of those codes would go down here in the console. Now, while these packages are loading, they pull and draw from other previously established code packages, and this process is known as dependencies. So RStudio will ask you, do you want to update some of these other packages as well? And my guess is for the setups that we have in our course, in our Bio 175 course, you could go ahead and select no. You do not need to install other packages at this time beyond the ones that are listed here in the tutorial. Continuing to follow the Neon tutorial, we're going to load these packages that they recommend. And because I always like to try to visualize the data using ggplot and other methods, let's go ahead and, like usual, load up the tidyverse. Many R programmers prefer that strings are not treated as factors by default, so you'll notice this here says to make sure that strings as factors is false. And if we do need to turn a categorical variable into a factor variable later, we'll do so manually. So we'll go ahead and load up those libraries. Now, what I thought we would do today is look on and see how we could download data from one field site. I should literally back up here. For Neon, Neon collects ecological data in various locations in North America, as you can see on the map on the screen. And what I'll eventually have you, the students, do is look at 3 of these sites. The reason why these sites were chosen for the broad science endeavor funded by the National Science Foundation is so we could collect ecological data in various climates and regions throughout North America. So what I thought we would do today is explore the process of downloading data from the closest site to us, and the closest site is going to be abbreviated SJER. SJER for San Joaquin Experimental Range. Now we're going to head over to the area on the Neon site where we could download the data. In particular, I like going through this route where we could explore the data products. It's a nice point and quick interface. Later on, if you go into a research capacity in studying ecological data, there are more efficient ways to extract data from those various sites. But we'll keep things simple for today. When talking about the ecological data, you could see that there are different types of data sets. Right here on the front screen, we have some wind speed, we have some air temperatures, we have some chemical compounds in the atmosphere, etc. And at the moment, Neon is claiming to have 181 products from their 81 sites over this time frame, which is pretty much the past decade. For today's exploration, we'll go down here to sites, and like I mentioned on the previous tab, we'll focus on the SJER, the San Joaquin Experimental Range. Notice that some sites, according to these numbers here in the middle, have more products than others, depending on how long the site has been running and what capabilities are available. For today's exploration and tutorial, oops, let me see if the website loaded correctly. Let me try it out again. I'm gonna select this one site, SJER. I'm going to click View Selected. And I'm going to, for today, focus on this data set here called the photosynthetically active radiation, PAR. And to make sure I found that, I typed in PAR into the search bar. We'll quick download data, which will take us to another website or another search function, but it will not make us download anything just yet. So here I want to make sure that for simplicity, only one of the sites is selected. Today that will be SJER. And you could see by the filled in boxes in this timeline, the data that is available for SJER started relatively recently in the last 4 months of the year 2018. For simplicity, we could go ahead and select all years for that one site. And in the upper right corner, you'll notice that for our convenience, the software will estimate the file download size. Compared to some larger projects, about 90 megabytes is not too bad, and it should only take a couple minutes to download. When we're ready, go ahead and click Next in the upper right corner. That will take us to a set of options asking us if we want documentation. It's a good idea to include documentation, especially if you're doing a research project and you need to cite your sources. Clicking Next. The third set of choices is package type. For our explorations in this course, go ahead and click the basic package types, and then finally agree to the terms and conditions of downloading the data. Fortunately, this is completely free of charge. Just make sure to understand that this is professional scientific endeavor to get all this data, and there are some terms and conditions. So now when we click download data, your browser will confirm that you do want to download the data. So my browser says it's going to be downloaded into a zip file called neon_par, par for photosynthetically active radiation. And we'll save this file. Now, out of my own habit, I always run a quick virus scan on whatever I download, even if I know where I've downloaded it from. So, just in case. Alright. Now, of particular importance, wherever you saved the RMD file for this tutorial, make sure you put the zip file, the neon par zip file, in the exact same place. Now, later on, when you're studying different sites, different locations from where the data came from, you're probably going to want to have a naming convention, name the file so that you could easily find the information. Since this information came from the San Joaquin experimental range, I'm going to change the name of this zip file to SJER. But I'm going to keep the par there just in case we need to recall that this is the photosynthetically active radiation data. Now, with a zip file, the convention is usually to unzip the data and see what you have. Fortunately, the Neon utilities that we loaded earlier will do that in a way that's convenient for subsequent calculations. And that command is stack by table. If you followed my advice to put the zip file and this RMD file, our markdown document, in the same place, all you have to put inside this set of parentheses and quotation marks is that name of that zip file, in this case sjer underscore par. So this will unzip the file in a way that's concise and organized, and it may take a couple minutes. So while that's loading, I'll go ahead and start explaining what we're going to get out of this particular step. The ecological data, the weather data, will be shown in a couple different tables. One of them is at 1 minute intervals, and another is at 30-minute intervals. When you're exploring data, just trying to get a grasp of what you have, it's easier to use a small sample of data, and that way the calculations will not take too long. And if you just think about it for a couple seconds, the 30-minute data is a lot more sparse than the folks who took the data at every minute. So the file for the 30-minute data will be a lot smaller than the 1 minute data. So now looking at what that stack by table function did, it created this unzipped folder for SJER. There's some documentation saying which scientists are responsible and maintaining the the site and the measurements. Then we'll go into this stacked files folder, and you could see some CSV spreadsheets. The README file has a lot of information to about how the files were named and organized. The sensor positions, if you're wanting to keep track of map making, literally knowing the longitude and latitude, then you could go into this sensor positions spreadsheet and double check that, especially if you're looking at multiple sites of data. When you have data sets that are fairly large, especially if they have many columns, you'll tend to have a situation where we have short column names here that makes coding and data analysis easier. But then a separate file like this one's called variables, that will more fully explain what each variable is. So say for example here for the 1 minute interval data, we have the longitude and latitude of the Neon site. We have the date and time when the information was collected. And for today, we're looking at a metric called the photosynthetically active radiation. So you see some statistics here. The mean, minimum, maximum, and variance. Some of these variable names will be used in the 1 minute data. The same variable names will be used in the 30-minute data. And what I mean by that, let's open up the 30-minute data. And those variable names are up here at the top of the table. However, depending on the site, depending on what the scientists have chosen, some variables may be empty, may not have available information. So you can see that this data collection started on September 6, 2018. And we were able to gather and download data all the way up to and including March 31st of this year. So that's 30 minutes over approximately 1.5 years. And thus, that's why 30-minute intervals. And that's why we have about 165,000 rows of observations. So a pretty sizable data set already. The 1 minute intervals would be about 30 times as big as far as the data set size. So looking at our measures for PAR, what we'll do today is focus on this column here for PAR mean, the average amount of photosynthetically active radiation in that time interval. So once again, that stack by table command, it took the zip file, unzipped the file, and arranged the information that was easy for us to point and click and navigate through. To be able to use the data for subsequent calculations here in R, like we've done elsewhere in our statistics course, we'll read the data into a data frame. There's another command here from the Neon utilities called read table Neon. And we need to be careful with these file names. So I have the files inside a folder called SJER-PAR. So I need to make sure that this part of the file name, namely the start of the file name, also matches what my naming convention for what I've been doing for the past few minutes. This code, labeled PAR30, will load the 30-minute interval data. We specifically say that's going to be our data file. And we also, at the same time, load the variable names, the descriptions of the variables, by pointing to the variables file. That will load up. The file, compared to other projects, is not too large. So we have the PAR30 here up in the upper right in our environment. And we could click on that name, PAR30, to get a glimpse of the data to verify that it has been brought into our RStudio session. So I hopefully or probably made that look easier than it is in practice. This is probably my third or fourth draft of running through this Neon tutorial myself. But hopefully we as a group can reach this same point together where we have installed the packages, loaded the packages into our RStudio session as libraries, and then loaded the data, first downloaded the data from the Neon website, and then loaded the data with these two lines of code. Now, when you're beginning a research project in an area that may be new to you, some good ideas to do is to get a grasp of what your data looks like and start to conduct summaries. Our data frame name is par30, and we'll wrap this with the summary command. And for today, we will focus on the par mean variable. So for whatever units par mean utilizes, we could see that the minimum is a slightly negative number, which means negative photosynthesis radiation, which might be an outlier or something of concern. The 25th percentile is at 0 radiation, median is at 4 units, but the mean 75th percentile and the maximum are relatively high numbers. Now recall that in the data frame, if you look at the top right here, we had about 165,000 rows. So back here, saying that there were about 6,000 missing values is debatable whether or not that's problematic. But I would argue that that's probably not too bad. Missing values might be very temporary blips in equipment failure or very um, tough weather patterns to collect the information in. To visually get a sense of the spread of the par mean variable, let's go ahead and create a box plot. We will send our par30 data frame, pipe it into a ggplot as usual. I'm going to put the par mean on the y-axis in the aesthetics. And then we'll have a box plot there. There'll be a minor warning here because we had that 5,790 missing values. Recall that we have in the past understood what a box plot does, and at the moment there seems to be a lot of outliers towards the top, which doesn't really surprise us compared to the summary that we just looked at. So what I think I want to do is to see if we could look at this information without the outliers. And that's debatable because in our region here in the middle of California, there are some very hot days and there are some very cold days. And that might play a role in why there were so many outliers in the first place. So we'll look at the quantiles. That is how we determined where the box and whiskers for the box plot are. Because there are missing values, we have to avoid the missing values, which the na.rm equals true parameter. And recall that I'm also putting in the 0.25 to say grab the 25th percentile. Let's do that a couple more times at the 50th percentile, which is the same as the median, and at the 75th percentile. Then from there, recall that the interquartile range is the 75th percentile minus the 25th percentile. And then finally, the top whisker of the box plot from the previous graph. That is the top whisker here at about y equals 1500. We could compute directly by saying the median plus 1.5 times the interquartile range. Now that avoids outliers, and let me show you how I would then redo the graph by avoiding the outliers. We'll filter the results where par mean is 0 or less. Or let's say greater or equal to 0. And then also where par mean is less than or equal to the top whisker in the previous graph. Be sure to make sure all of our syntax, what we type in, is error-free. And it's not quite obvious here, but at least the y-axis has a collection of arguably more reasonable numbers. Following good habits, let's go ahead and label the graph. I'm just going to give this the title, A Box Plot of Par, knowing that in the subtitle I can explain what par is. In the caption, that's where I usually like to put the data source. Here the data source is Neon. My current gripe with this graph are these meaningless numbers along the x-axis. So one hack that I tried out to get rid of those is back up here in the aesthetics of the ggplot layer. I fixed the x-axis at x equals 0. And that didn't quite do anything. but we could look up quickly how to get rid of the x-axis numbers if need be. And especially if we have multiple box plots, we should label from which site each box plot came from. So I just Googled how to remove those numbers. So let me remove the x equals 0. That was not the correct way to do this. Instead, we're going to focus on the theme. And say along the x-axis, have a literally blank element there. It's always fun doing live coding, isn't it? And we'll remove the text and tick marks from the x-axis to clean up the graph a bit. One more exploration I thought we could look at today is a line plot. That is to see if we could spot any trends in the data over time. We're going to pipe in our data frame into a ggplot. Looking at the data frame itself, you'll notice that the times for each time interval have a start time and an end time. But in particular, note just literally how the name is spelled. So we're going to have a start date time on the x-axis. And then we'll once again have par mean on the y-axis. For a line plot, the command is gonline. Yeah, and maybe change the color a bit to jazz things up. So you could see that, especially with the dates at the bottom of the screen, that the photosynthesis active radiation goes through some sort of sinusoidal trend, some sort of wave pattern that we would suspect correspond where the valleys correspond to winter and the peaks correspond to summer. Let's go ahead and label the graph. Now, on the x-axis, depending on your audience, you might consider these labels 2019 January, 2019 July, etc. to be pretty self-evident. So when the axis tick labels are pretty self-evident, I'll go ahead and get rid of the word or the variable name on the x-axis to clean up that part of the graph there. And like usual, we could do stuff like theme minimal to get rid of the gray background if you prefer. Alright, so I'm actually gonna call it there and end this part of the tutorial. If there is demand or depending on where our research goes, we'll come up with more ideas and maybe more videos in the future. Thanks for watching, and I will see you next time.